Here we will start from the Schrodinger equation of a one-particle system, and we want to derive in the classical limit something related to classical mechanics. So we want to show that we can derive classical mechanics from quantum mechanics. In order to do that, I will have to define psi of RT, which is a function, of course, which depends on the position of the particle and time. I will define it to be some constant a times an exponential e to the I s of rt, which is some function that I don't know, divided by h bar. So I'm simply rewriting the problem in terms of the function s, because if we substitute this expression here in the Schrodinger equation, we will find an equation that should be satisfied by the function s, and therefore we are just shifting the problem from psi to s. And if you take a look at this expression here, h bar should have the same units as s. So it means that s is an action, because h bar has the same units as action, because h bar is energy times time. So if we replace this expression right there instead of psi, we just have to do some calculations, because we have to calculate the Laplacian of psi, and we have to calculate the Laplacian of this expression, which is just a calculus exercise if you want, and you have to calculate the derivative with respect to time of psi, which is a simple exercise. And then you will find that you can also cancel this constant here, because it appears here on all those terms, and you can factor it out and cancel a, and you can also cancel this complex exponential, because it also factors out of all those terms. So what you basically find if you do this substitution is the following equation, which is to be satisfied by the function s minus the derivative of s with respect to time equal to 1 over 2m, and here we have the magnitude squared of the gradient of s. I could have written it like this as well with straight bars, but doesn't really matter, minus I h bar divided by 2m times the Laplacian of s plus the potential energy, which depends on the position of the particle. Now what we are going to do is we are going to assume that the term that multiplies h bar here is going to be neglected. So it's as if we set h bar approximately equal to 0, which is something that can be done in classical mechanics. After all, h bar does not appear. So h bar is something that tells us how energy is quantized, for example. So if we set h bar equal to 0, it means that we do not have quanta anymore. We have something that's going to be continuously distributed. This is something that can help us find something related to classical mechanics, not anymore to quantum mechanics. And if we do that, this term here can be neglected. So we are left with this expression, minus ds over dt equal to 1 over 2m gradient of s squared plus v of r. Now this looks actually quite familiar, especially because on the right hand side of this expression, if we, for example, set gradient of s equal to some momentum p, this is exactly the Hamiltonian, because we have p squared divided by 2m plus v of r. So this would be an Hamiltonian that depends on position r, and instead of momentum p, we have the gradient of s. And this is also known as the Hamilton-Jacobi equation. And it can be derived also from classical principles. So how can we derive this equation here? We can derive it from the action. The action s is a function that depends on time, but it can also be considered as a function that depends on the position at time t, because we have to integrate a Lagrangian that depends on position, velocities, and time. In this case, I will indicate time as t prime. So here we have dt prime. And we have to integrate from some initial time t0 to some final time that I will call t. So we have a trajectory, and in general, when we want to consider the Euler-Lagrange equations, we fix the endpoints here and we let the trajectory vary, okay? And then we can find the Euler-Lagrange equations when we set the variation of s equal to 0. But in this case, when we want to find the Hamilton-Jacobi equation, we also vary the endpoint here. So when we consider the variation of s, we have to vary the coordinates, so we have to vary r, but also the velocities, r dot. So what we find is integral from t0 to t, the gradient of L, in this case I will write it like this, gradient with respect to R, and then take the dot product with the variation of R, plus the gradient of L with respect to R dot, and take the dot product with the variation of R dot, multiply by dt prime. Now, what you can do, you can rewrite this term here, because R dot here is the derivative with respect to time of the position, R, and this term, you can manipulate it like this, the derivative with respect to time of dl over dr dot dr minus, so this is the derivative with respect to t prime, minus the derivative with respect to t prime of dl over dr dot product with dr, and then you can substitute it there, and you can rewrite the variation of s as integral from t0 to t. We have dl over dr minus d over dt prime dl over dr dot product with variation of r, times dt prime plus dl over dr dot product with dr, and we have to evaluate it between t0 and t. This is the Euler-Lagrange equation here, so this is equal to 0, and we are left with this boundary term here. In the case of fixed endpoints, this would be equal to 0 because the variation of r is equal to 0 at the endpoints. But in this case, when we set t prime equal to t, this term here will not be equal to 0 in general. So we have the variation of s equal to dl over dr dot product with dr at the time t prime equal to t. So from here we find that ds over dr is equal to dl over dr dot. If you recall from classical mechanics, this is also equal to the momentum p. And also we can take the derivative with respect to time, the total derivative with respect to time of the function s. So the function s depends on time, but also depends on the position at the end point, r of t. So this is ds over dt, the partial derivative with respect to time, plus ds over dr dot product with r dot. And now from above here we find that ds over dr is equal to momentum p, or dl over dr dot. Now I will just replace it with p. Also, you know that the derivative of s with respect to time is equal to the derivative with respect to time of the integral of the Lagrangian over dt prime from t0 to t. And this is of course equal to the Lagrangian itself. So we can rewrite from this equation here that minus ds over dt is equal to p dot r dot minus l. And this is of course equal to the Hamiltonian of the system. So we have found exactly what we expected, the Hamilton-Jacobi equation. So we derived this equation also from quantum mechanics. And it means that quantum mechanics, in some kind of limit, when h bar can be considered as negligible, contains classical mechanics. And this happens not really if h bar goes to 0, because we cannot really do that. H bar is a constant. We have to consider this. So it's h bar times the Laplacian of s should be much smaller than the gradient of s squared, the magnitude of the gradient squared. So let's say that this ratio here should be much smaller than 1. So if this happens, we are in some kind of a quasi-classical limit.